We are going to start our next chapter, which is chapter 6 and on graphs. Now this chapter will look at a couple of visual representation of the data, right? I'm sure that we have all been exposed to many different sort of graphs, and this is like a refresher for most of you. So again, when we try to draw something on the paper to represent some data, so we try to, most of the time we have some scales, right? For an example, let's say here we have a scale, and in every single time we draw the graph, we use some sort of scales. We use sometimes like something called graph paper, where also we have some scales. And in scales, if you see all the major and minor ticks, for an example, these are called major ticks, and these are called minor ticks. If you look at all of those, you realize that every single ticks actually has a numeric value, right? So for an example, this is 0, then 1, 2, 3, but we don't write each and every number, okay? Because we can just see and we can count and we can understand those numbers. So this is important to understand that everything that will not have label, but there will be some labels, some numbers to indicate something, and then we'll be using those to understand the remaining ones. For an example, we have these numbers like 0 and 5 and 10, because those are the ones which are related to these major ticks, major divisions, okay? But there are some incremental minor divisions like this one, right? Like this one, these are like 1, 2, 3, so, and then after 5 again 6, 7, 8, 9, so these will be the minor ones, and these are the major divisions. And then you will be the one who will be determining which one will be the major ticks and which one will be the minor ones, right? Based on what will be your data and how you want to present the things, right? For example, let's say the major divisions on a graph are labeled, for an example here, 0, 5, 10, 15. These are all the major ones, right? And if you look at the ticks, those are a little bit bolder and longer than the minor ones. But the number of blocks between the major division is 5, because if you look at here, see, this is 1 block, 2nd block, 3rd block, 4th block, and 5th block, right? So there are 5 blocks. That means if you just divide, so the difference of these two, major division is 5, right? 0 to 5, or like 5 to 10. So between each major divisions there are 5 difference. There is a difference of 5. And inside there is a minor division of 5s. So that means each division will stand for 1, right? But it will not be the case every time. I'm saying this is the case for this specific scale, okay? It's possible that one minor division might represent 2, might represent 10, might represent 100, based on the major and minor. So all we do is we just divide the difference of two scales, which is 5 here, by how many minor divisions you have. So we have 5 minor divisions, and we have 5 difference of 5. So divide 5 by 5, get a 1. That means each minor division is exactly equal to 1, right? But it may not be 1 in other graphs. It depends, right? Okay. Now, to plot the graph, because once we have the data, we try to plot the graph. We have plenty of different types of graphs. The reason we try to plot the graph, first of all, is try to make a visual representation of the data, which makes sometimes more sense than just looking at the raw data, because we can understand and get the summary or of interpretation of all the data right away just from the graph, instead of looking at the raw data. Okay, so to plot the graph, what you do is you just, most of the time when you plot the graph, you will have 2 different variables. So one of the variables you will actually identify as independent variable, that is called controlling factor. One will be the dependent variable, and we select the suitable graph paper. We label the axis, because we will have 2 different axes, right? So let's say, most of the times what happens, you have a vertical, a horizontal axis, which is called most of the time x-axis, right? And a vertical axis, right, which is y-axis. So the independent variable is plotted, along the x-axis. independent variable, whichever you think independent, right? And the dependent variable is plotted along the y-axis, which is the vertical one, okay? And then we label them because we just try to make sure that the reader understands which axis stands for what, right? And then we assign the values. We draw the major and minor ticks, right, based on the data we have. For an example, let's say here is a type of graph paper we have, but we just want to show you that how different that can be. For an example, this is a graph paper good for, let's say, if we try to measure the time passed versus temperature in degrees. For an example, let's say we are trying to see how a device or equipment is having different temperature in different times. Maybe it's getting hotter over the times, right? So we want to measure that. So this might be a great graph for that, because let's say along this line we are actually we are labeling the times in hours. So this is like 1 hour, 2 hour, first hour, second hour, third hour. And along this line we have temperatures. Do you see the difference along the the major and minor ticks? Look at this here. It's 10 degrees, 20 degrees. Because it doesn't make sense if I just put 1, 2, 3, 4, because the temperature can be much more than 1, 2, 3, 4, right? And here it makes sense. It's just 1, 2, 3, 4 because those are hours, right? So we can also count the minor deviation. So this is just the 1/5 of an hour, which may be like what, 12 minutes? 1 hour is 60 minutes, right? So 1/5 of an hour, 12 minutes. But here, one minor division is what? One minor division is what? 2 degrees, right? 2 degrees, possibly in degree centigrade, not in Fahrenheit. You know that there are several other the degree measuring scales. But for an example, let's say you are having a completely different thing. For an example, let's say you are having 3 different types of lumber made of pine, oak, and cherry, right? And then you are trying to see the average cost of lumber for each different types, right? So this might be a great one for that, because you see here we just classified pine, so we might be plotting something for pine here, oak here, and cherry here. Okay, and then this is the dependent variable, which is the cost of the lumber, average cost. One of the things that I want you to note here is, look at this here. This line is actually sequential, right? Because you see the hour, 1, 2, 3, 4, those are in sequence, because you cannot just write 4 before 3, right? It has to be 1, 2, 3, 4, 5, 6 in sequence. But look, notice here, these 3 doesn't have to be in sequence, because you could have started with cherry, right? Do you see the difference? You don't have to start with like pine. I'm saying you can. It just it depends on which one you want to present first. So that kind of thing, that it depends on what exactly you want to present. And you see here, we actually tried to make these minor deviations much bigger, right? Because even here, this minor division doesn't make much sense. For an example, let's say this is the point for the pine. What is this point? What is this point? This doesn't make any sense. I'm saying we just try to draw probably something for pine here, or maybe some sort of bar graph, right? Something for oak here, something for cherry here, but there is no meaning of the minor division along the x-axis, right? So for an example, let's say this is let's say my line graph I have drawn, let's say for my class. So let's say I have taken a couple of quizzes, and using a graph I want to see how my students are performing in my class, average score. So these are the number of quizzes along x-axis, and these are the number of score here. Okay, you see we started from 70, and at some point it has fallen, and again we are pretty much like up and down, but over the time we are a little bit rising, right? Because you see here we are getting a little bit better. So this gives me a lot of indication of how we are performing in our class, instead of just looking at my raw data from my, let's say, my grade book. You know what I'm saying? So this is like this is called a line graph. It's the same thing, but you know, it's a little bit different. So we see a linear scale there. This is a bar graph. So this depicts the data by bar, by heavy lines, because you see here, this is called actually a histogram in statistics, which is a graph of frequency, meaning number of occurrences by group. For an example, this is a representation of the age of underground storage tanks. Now let's say these are 5 years old, these are 10 years old, and along this line, this is the frequency, meaning the number of tanks. Let's say for an example, for a specific location in Shelby County, we are just trying to see how many tanks we have with different ages. If you look at these graphs, what do you notice here? You notice that most of the tanks you have, storage tanks, are of age 10, right? Because this is the tallest bar, right? And the least of the storage tanks are pretty much like 30 years old. Right? So you can make some sense that most of the underground storage tanks, what are their ages on an average? So most of the most frequently occurred ages are like 10, right? This is called a circle graph. Some people call it pie graph. Okay. In the circle graph, we actually divide the circle into different segments. Okay. Each of the segments actually represents different part of the data. So we assume that the total circle is 100%. So for an example, let's say this is probably a business organization's cost distribution, that how they are spending. For an example, if you look at here, the most of the cost they're spending for the factory payroll, right? And the second highest is the other business expenses, and then they're spending 20% for the supply cost, and then they're also managing an office support payroll 10%, and then 10% for the engineering payroll, and then this is actually the 100% they're earning, but they're actually they're pretty much, just by looking at the graph, is visible that they're pretty much spending 95% of their earning in some different categories, except this 5%, which is their profit. Right? I'm saying, this kind of graphs are also very important. But this is a good representation, because here you see here, for this representation, the pie graph or the circle graph might be the best choice. Right? So this is still the same thing. We tried to show in a different. Now, for an example here, let's say if we have to answer a quiz question, let's say this graph is given to us, okay? And what it shows is, in every month, you see here, these are the different months: January, February, March, April, and these are the number of automobiles. Now, what happens is, let's say this is a car dealer. This is a car dealer, okay? And their projected sale is the gray bar, and the actual sale is the black bar. For an example, in the January, you see their projected sale was 26, but they were able to sell what? 21, right? In February, they projected 11, but they sold even more than that, right? So that's kind of thing. So it's just a projection and the actual sale for, say, a 6-month period. Now, for an example, let's say if I have to answer this question, what is the total number of cars projected to be sold during the entire 6 months? All I have to do is I have to add the number associated with all the gray bar, right? Let's say for the first one, 26. For the second one, 11. For the third one, 18, right? We'll be adding all of those to see what is the projected. What is the actual car sold? We'll be actually adding the numbers associated with all the black bar. Right? It's pretty easy. So for each and every month for 6-month period. What is the average number of cars sold per month during the entire 6 period? So it's just dividing by 6, right? Once you know the total, meaning all the black, coming from all the black bars, summing it up and then dividing by 6, because it's just a 6-month period. So that will give us the average cars sold for the 6-month period. Now here is another example, given a circle graph for an example. This indicates, this actually represents the causes of death of ages between 15 to 25, pretty much in young ages. So its total is 1,000 fatalities we have on our list. So as you can see from here, 10% is out of is of disease, 15% of drugs, 35% by auto accidents, and 100 fatalities of suicide, and the remaining ones are accidents. As you can see, some of these are not exactly given in percentage. Let's say this is a quiz question and you have to answer some of the questions. Now let's say if I have to answer how many people died from automobile accidents. First of all, as you can see, automobile accidents, the people are dying from what? The dying was 35%, right? So we have to find, so what is the base given here? Let's get back to the percentage problem. Base is what? 1,000, right? Because the total fatalities are 1,000. The rate given is what? 35%. So the portion is unknown. If you have to find the portion, the formula was what? Base times rate. So that means 1,000 times 0.35, because percentage can be, converted to fraction. So that will give you what? 350, right? So pretty much you will know that 350 people died by auto accidents, right? From this graph. Can we answer this question? What is the percentage of fatalities caused by the suicide? So as you can see, the suicide, we have 100 suicides, right? Now for this problem, this is again a percentage problem. The base is 1,000, portion is given, which is 100, but you don't know the rate. To find the rate, we will be using the same, we are just going back to the chapter 4 and using the formula from there. So it's just the portion by base, portion over base, 100 over 1,000, which will give you 0.1, that means what? 10%, right? What is the percentage of the fatalities caused by non-auto accidents? Now you can see here, this was, remember, every single time the circle will represent the 100%. So this is 10%, 15%, 35%, and this is 10% again, right? So what is the remaining percentages we have? 30%, right? If the total is 100%, that means non-auto accidents are 30%, right? So we can answer all these questions just looking at the graph, right? So that's all we have for today. This is a small chapter, which is chapter 6. So I'll stop my presentation here and we'll try the quiz, meaning the homework for chapter 6, okay?